Hello, in this video I'd like to talk a bit about a debugging project I made for myself recently, namely this box. Its purpose is to debug slow speed digital signals by using push buttons to set a signal state and LEDs to read a signal state. Its functionality is best demonstrated when powering it on. For now let's take 24 volts. As we will see, it will take a whole voltage range as input, but for now use 24. So this is what it looks like, nothing on the back side. On the front, two ground terminals, that's the blue terminals right there connected to each other. For each channel there's a yellow terminal connecting the I/O signal to measure and to control. We'll look at that later. Top right is a VCC input, which is basically the main voltage input corresponding to the I/O voltage on each channel. And for cases where VCC is lower than say 7 volts, we use a separate 5 volt input for powering the digital logic within this box, as we will see later. Now let's take a look at the rightmost I/O channel, corresponding to the rightmost switch, the rightmost LED and the rightmost terminal. The voltage at the rightmost terminal is always indicated by this LED. So if the LED is on, voltage is high. We can make the voltage low, drive it low, by pushing the switch. So the box applies low voltage. It does this with a certain output impedance, so you can override it from the externally, right? So you can set the voltage, you can set the signal level, and you can read it using the LED. Furthermore, it has a function switch. As you can see now, the switch behaves in a high active fashion. So normally the I/O voltage is set high. If you push a switch, I/O voltage is set low. You can hold the function switch and press the channel switch to toggle the polarity. Now it's a low active. Normally voltage is low. If you activate the switch, your voltage is high. Likewise, like we said, you can apply an external voltage here, and the level is indicated by the LED. On is always high, off is always low. Alright, so that's basically how it works. How you use it. Now the rest of this video we'll take a look at the schematic. I'll take a look at what's inside this box, what it looks like. Then we'll go back to the schematics and take a look at power input, the voltage regulation, and the microcontroller in here. And we'll also take a look at the component values chosen per channel, because that's maybe nice. After that, we'll take a look at what's going on inside when we drive an output high and low with respect to heat dissipated in resistors. I'll show that on the infrared camera. We will see how a load impedance has influence on the voltage at the I/O channel. In other words, we'll see how what the influence is of the output impedance of each channel. We'll see what the minimum, we'll measure what the minimum I/O voltage is in order to drive the LED in order to drive the LED high. Then we will do a bit more measurements, but that's basically it. So show how it works, show what it looks like inside, what the schematic is. And finally we'll take a look at the software that's running inside this in not much detail. Okay, so schematic looks something like this. We'll just do the schematic for each channel, and this is duplicated 4 times for 4 channels. First is the output stage driving the I/O channel, which is basically a transistor, open collector output being pulled up by a resistor. Another resistor for protection, as we will see. This point is VIO, that corresponds to the yellow output terminal. Let's take the rightmost channel. We'll do the measurements on the rightmost channel as well. Then there's an input circuitry to simply drive an LED. There it is, and the voltage here is V logic, let's say that. V logic. Voltage here is VCC. We'll call that VCC. One of the requirements is that this box is usable for voltages, so external voltages in the range of 3.3 volts up to 24 volts, because that's what I normally use. So that's basically how it works. So this leftmost side is the output drive. It drives the voltage on the I/O channel, the I/O pin. This is the input circuitry. It shows the state of the I/O pin using an LED. Very simple. Right, let's take a look inside. Conveniently, I already took the cover off. Unscrewed the box for your convenience. This is what it looks like inside. Alright, if you can see that. There's no PCB, there's something like this. It's a Vero board or a strip board or Vero board or whatever it's called. I use copper islands of 3 pins, three holes. It's convenient for me. As you can see, there are, let's count the pairs of resistors. There's 4 identical circuits at the bottom. That's the drive and the input circuit of each I/O channel. The big resistor that you can see there are for the output drive, and the small resistors are for the LED and for the input circuit. And each I/O channel corresponds to 2 transistors that you can see here. And also, there are not many wires used on the board itself. There's obviously wires coming out, but I think it's a little bit of a challenge to use as few wires as possible. So, and a strip board like this is nice for that. It can help with that. So it's a nice puzzle. So furthermore, if this thing will focus a bit, yeah. Furthermore, there's a 7805 linear regulator right there that converts the input voltage to something usable by the digital logic. There's a diode. What 2 inputs can go to 1 output for the logic voltage. Capacitor. Wires going to switches on the front panel. It's just an aluminium plate with holes drilled in it. Switches and LEDs, as you can see, and 4mm terminals. And also, there's a homemade general purpose microcontroller on a board, and it basically does a debouncing, the switch debouncing, and the logic of the function switch, the behavior of the function switch within this box. So that's that. Now let's leave this thing right there and go back to the schematic briefly. And let's take a look at different component values. How to determine the component values of everything that you see here. For transistor, it doesn't matter, we'll get to that later. First of all, let's take a look at the value of this resistor right here. So this is the resistor between the digital I/O channel and the base of the transistor controlling the LED current. Now for the transistor, I use the BC547, which is a general purpose NPN transistor. It has a gain, that's an beta or gain. That's an amplification between base emitter current and collector emitter current. That's approximately 100 for this transistor, and that's quite pessimistic. It's probably more, like 250 or 200. But for now, let's take 100. Now, if we consider V logic, as we will see, is 5 volt. Let's say there's about 2.5 volt of drop over this LED. And if you choose this resistor 220 ohm, that means there's 2.5 volts over this resistor, causing about 10 milliamps of current through the LED when it's on, when the transistor conducts. Now, because of this gain, transistor will start to regulate the current through itself from collector to emitter if the base current drops under 1/100th of the collector current, right? So in order to prevent that, in order to have this resistor here limit the collector current instead of the transistor itself, we would like to have this current into the base higher than 1/100th of that current, which is 100. So this current should be bigger than or equal to 100 microamp. 100 microamps. Now, as we said, I want to use this box for voltages down to 3.3 volts, somewhere around that. 2.5 will be nice. Let's say, rough estimate, let's say there's 0.7, or let's say there's one drop of voltage over the base emitter junction of the transistor. So in other words, let's say there's, for convenience, 2.2 volts over this resistor or more, and that would be with VCC voltage of 3.3 volts, which has to cause 100 microamps of current. So in other words, this resistor has to be at most 22k ohm. Right? If we choose this resistor more, the transistor will be limiting the current, and eventually what we would see is the LED dimming down with lower VCC, and we don't want that. Okay, so much for the value of that resistor. Let's undo that. So, the value of these resistors, this one and this one. Now you want to have these resistors pretty small, because there's a balance, but small because this box, this is the output circuit of the box, this drives this I/O pin to a certain voltage, either low when the resistor conducts and this voltage is made 0 basically, or VCC if the transistor doesn't conduct. So you would want to make these resistors small because you want to apply a certain strength while driving the I/O pin. However, you don't want to make them too small because the transistor can take an unlimited amount of current, and you want to protect it a little bit. So situation in which you want to protect it is when this transistor conducts, right? So it's driven high, and the current flows here, and you choose VCC to be pretty high, namely 24 volts, then you want to limit the current here somewhat. Now let's start by choosing a 1K resistor. This has 24 volts applied. Let's assume the collector emitter resistance is 0 ohm. It's not, but for the sake of argument, let's assume that. 24 volts over 1K is 24 milliamps going to that resistor. Now the power dissipated in the resistor is voltage times current, which is 24 times 24, which is approximately 600 milliwatt, so 0.6 watt. So let's take a resistor of 2 watts, which is 3 times that power it will be dissipating, and to be safe. Okay, so 1K 2 watts. For this resistor, let's take the situation where this transistor conducts, so it's full on, so the collector emitter resistance is basically 0 or very low, and someone applies a 24 volt to this I/O pin. You know, the box shouldn't break down, so this resistor should be big enough to protect the transistor from that current that will be flowing then. Right, so it's the same story. You have 24 volts here, ground there. That will certain current will flow. So if you choose this resistor 1K 2 watts as well, it will dissipate 0.6 watts. And if you choose a 2 watt resistor, it's more than enough, as we'll see. So that's basically it. Now that was the analog part of the circuit, basically, or at least the I/O side of the circuit. There's as you see, there are 3 voltages with VIO, but 2 voltages, V logic and VCC. Now VCC is the main voltage, I mean corresponding to this output pin, so it's basically the voltage to drive this output pin if you choose to do so. V logic is simply, well, we choose it to be 5 volts to drive the LED with a constant voltage, so that you don't see a difference in intensity. And also to drive the microcontroller, to power the microcontroller. 5 volt is nice voltage. So how this works is basically this. You have VCC as an input to the box. It goes into a 7805 regulator, linear regulator. There's a cap here. I think it's 10 microfarad electrolytic or something like that. Output goes to V logic. Right. This regulator will start to drop out. No, I'll put the board a bit higher. This regulator will start to drop out at voltages of about 7 volts or 6.5 volts. In other words, if VCC is lower than 7 volts, say, then the output V-logic will start to drop, and we don't want that. So what we do instead is make another way to provide the V-logic through, let's call it auxiliary 5 volt input. That's actually that second input here. You cannot see it, but under the VCC input at the top right, there's another another power input which is called 5 volt. Creatively. Right, so that's how it works. These diodes are here to prevent. If this diode would not be here and you provide, let's say, 24 volt, well, that's not cool, but let's provide 5 volts here and you don't provide any VCC, there would be current flowing back maybe into the regulator. So I don't want that. So to prevent current flowing back into a voltage source, let's put these diodes here. You will have a diode voltage drop of 0.7 volt or something like that between V-logic and actually applied 5 volts, but that's not a big deal because that voltage drop has no influence on any voltages that you're going to measure. It's just the power little LED and the microcontroller. They can run off 4 volts or 3.5 or 3, that's fine. Okay, so that's for the power input. Now the microcontroller itself is sitting between switches, 5 switches, and 4 times the control voltage, which is basically the voltage here. Yeah. So microcontroller is grounded, takes its power from V-logic, and it's basically sitting between switches and output voltages, or switches and input voltages to the drive circuit. So I did this to make it more flexible. You can also hardwire switches to either a VCC or V-logic or ground here, but it's easier to have a microcontroller there, I think, because of, now you have a 5-button user interface, so you can do whatever you want. So I chose to have that polarity switch with function switch. So if I at some point decide that I want to be able to give pulses, or I want signals to be latched and display the latched signal value or something like that, I can simply extend the software here instead of toying about with changing the circuit. I think that's easier, but that's just my point of view. But for now you can assume this switch to be here and choosing between V-logic and ground. So and you can compare it to that if you want. Right, so that's the microcontroller stuff. Did that. Interesting thing maybe is because we have these big resistors right there and right there, and they are not rated 2 watts for nothing. They have to dissipate a certain amount of power, 0.6 watts as we saw. Now let's see what it actually looks like on the camera when they dissipate that power. So to get a feeling for what 0.6 watt into a resistor is. And for that I used this guy. See if that makes sense. So right now we have all outputs high, which means that the resistors that you just saw are not dissipating any power because there's no current flowing. Now let's change the polarity of one I/O channel as we saw. So this I/O channel is now low, which means the output circuit is driving it low, so it's conducting a lot of current through the transistor, and the resistor will become hot, as you can see. Right? Actually, I highly recommend you getting an infrared camera or something like that, or a FLIR 1 for your phone, because it's a really brilliant debugging tool. It saved me a lot of time already. Now as you can see, the thing that's getting hot is the resistor there. I can touch it with my finger, no problem. Touching it right now, and it's been on for just a little bit, but I can maybe feel it getting warm. It's not a big deal. Looks dramatic, but it really isn't. So this is fine, right? Now, as we saw, there's this. Let's put that there. There's this input resistor, right? Let's take a look at let's take a look at what happens if you use this I/O pin to drive your circuit. So you use the box to drive your circuit. You connect your circuit as an output of this I/O pin, which means basically that you're connecting a resistor. Let's call it R load at the output pin. Now what you see is two resistors being in parallel basically, because this resistor through the base current is conducting current, and this one as well to ground, both to ground basically. You have a resulting resistance of two resistors in parallel. You cannot make your load resistor as small as you want, because then what you'll see is that the voltage at this point will be dropping. Basically we have, if you consider this node, the output impedance of this box is either 2K if it's driving current, if it's driving this output pin to VCC, or 1K if it's driving it, pulling it to ground, right? So 2K or 1K. Now you can make a little table, our load, and percentage of drop. And what do I mean by that? Let's see how much percent of the VCC voltage will be dropped inside the box. In other words, what's the decrease of the how much is VCC decreased? How much is the voltage at this node lower than VCC? That's what I mean. Okay, so for RL, well, if you have an infinite resistance here, like a 10 meg ohm or 10 gig ohm or whatever, you basically have a voltage divider of, let's say, 2K on one side and 22K on the other side. So that's what, 1/10 or something like that, even less. So your voltage drop would be smaller than 10%. Okay. If RL is 22K, let's say, you basically have two 22Ks K resistors in parallel, which is 11K, 2K on one side, 11K on the other side. So that's basically the drop is 2/13, which is basically 15% or something like that. 15%. Let's say that, guesstimate. If you put 10K here, if the RL is 10K, the value of this base resistor becomes less important, because this value starts to become much lower than this one. So in a parallel circuit you can ignore the bigger resistor if the difference is really big. So, well, let's not just do that, but the 10K and 22K in parallel is about 7K, so you would have a drop of 2 divided by 9, because 2 plus 7 is 9, 2 divided by 9, which is about 25%, let's say that. And then, well, in the case RL is let's say 2K. 2K is getting a bit silly, because you can now ignore this 22K resistor. It doesn't influence the parallel resistance of 22K and 2K. The 22K is really much too big. So you now have a voltage divider on one side 2K formed by these resistors, on the other side 2K formed by RL basically. So the voltage at this node would be about half of VCC, and that's getting a bit ridiculous. Now note that you can always, if you have a circuit with a fairly low input impedance and you want to power it with this box anyway, you can always crank up VCC, right, to compensate for that, right? So it makes sense to have a multimeter sitting at this point to make sure that the voltage from driving this node high is exactly what you want it to be, but most of the time it's okay, right, because there's always some margin. Let's keep this table here and let's test that a bit. Let's test it using this box. It's not a decade box, a resistor decade box, but it's something like that. So there's a lot of switches. Unfortunately they're all black on a black background, but the only switch down in the downwards position is a 4 mag switch. So what you can do is switch individual resistors, enable individual resistors, and let's say that, and the switch in the upmost position is the resistor disabled, switch in downward position is enabled, and the total resistance of this box between the red and the black terminal is the sum of all the resistors of which is switches in the downwards position. I forgot one switch, I see. So this is now 4 meg, which is basically infinite. Let's put that at, let's drive that high, put that voltage at the input, and let's measure that voltage using multimeter. Right, it's not convenient. 22 volts. Now, as we will see, actually, if we disable this whole resistor, so now the resistor is infinite, it's still 22 volts. Why is it not 24? Because the VCC is 24 volts. Well, if you look at the schematic, if you follow the track from the trail from VCC back to ground, you see a resistor of 1K, 1K. This is infinite, RL, 22K, and it actually conducts current because there's a current flowing through this base. So basically you would have 1 volt drop over this resistor, right? 1 volt drop over this, 1 volt drop, 22 volts drop over that, and a little bit over the base emitter junction. Because the sum of this is 1 plus 1 plus 22 is conveniently 24, right? So that's why we see 22 instead of 24. Likewise, if you drive this output low, right? If you drive this output low, there's 0.11 volts, and that's so now the voltage at this node is 0.11 volts. Why is it not 0 volt? Because we basically have this transistor grounded. Actually, we don't have it grounded. We have it conducted. We have it full on. So this is V logic now, right? So this transistor conducts. So current is flowing here. It's pulling this voltage low. So it's not 0 because the collector emitter junction doesn't have a resistance of 0 ohm, right? If you measure at the collector, which we will not do now, but which I did, you will measure about 0.1 volt here, right? So that's why you can never pull it completely to 0. In practice this is not a problem because most, if not all, circuits consider 0.1 volt to be pretty much 0, right? But what were we doing? First, what we'll do is connect different values of RL. We just saw infinite, and then we saw a small drop. Right. Yeah, 10% exactly, because you have a voltage drop over these resistors because there is current flowing through this 22. That was a 2 volt that we just saw, right? So for 22K we would expect a drop of about 15%. So let's connect 22K there. That's 20K and 2. This box now behaves as a 22K resistor. Let's not drive it low, let's drive it high. So you'll see a voltage of 3.4 volts now. So it basically, that's, I didn't calculate it, but it sounds like 15% of 24 volts. Or, yeah, 22 volts. So, of 24 volts, yeah. 10K, next one. Right, this box now behaves like a 10K because the 10K switches down and all the rest is up. Say 18.6 volts, so that's starting to look like 24 volts, 25% sorry, drop inside this box, right? So the voltage is dropping now from, what was it, 22 to 18.6. On the extreme case, let's connect a load resistance of 2K, which is a bit ridiculous. Let's see, 2K is on, 10K is off, so this box now behaves like a 2K resistor, and indeed you see the voltage dropping to about half of VCC, right, 11.5 volts, yeah? So that was that. And that's great. Let's disconnect that. Let's disconnect that. Let's take a look at the minimum I/O voltage that you can apply at this point. We saw that, right? Let's take a look at the minimum I/O voltage that you can apply at this node in order for this LED to still, for 10 milliamps to flow here. So if this voltage gets lower and lower and lower, at some point this transistor will start limiting the current instead of this resistor. And what you'll see, if it does that, is that the collector emitter junction is no longer near 0 ohm, but it starts gaining resistance. So the voltage drop over the collector emitter will start to rise. So basically, if you look at the collector voltage while turning this voltage at this node down, you'll see that at some point it will start to rise dramatically, and at some later point we'll start the LED to become we'll see the LED become dimmer. So let's do that. Let's connect the multimeter to the collector voltage of the input transistor, like that. Now let's take another power supply. Let's start by spoiler. Right, let's start in a safe region, right? 2.7 volts. So that's not right. Live debugging session. Yeah, it also helps to connect the power supply to that box. Right, that's quality video here, right? So, under normal circumstances, what we see here on the DMM is the collector voltage of the output transistor. So not the output transistor, the input transistor. So collector voltage here on the DMM. Yeah, and what we're doing is lowering the voltage at this node here. And right now it's 3.2 volts. And collector voltage is still fine. LED is still on bright. So let's make that a bit less. 3.5. It's still okay. 0.1 volt. I call it okay. 2 volts. 0.12. Starts to rise a little bit, but it's still okay. Now if we go down, now it starts to rise a bit dramatically. Still 0.15, so it's not a lot. But if you go down like below 1 volt, so now it's already half a volt. 1 volt, 1.24, 1.25, 1.5. So now the collector voltage is about 2 volts. And what we'll see if we go lower is this LED getting dim, right? And that was the whole purpose, to keep the collector voltage low, so the LED, or the voltage over the LED is still high. The LED is still on bright. So actually, the estimate that this box is usable for down to 3.3 volts was very pessimistic actually, because it still works fine at 2.5 volts or even 2 volts, right? So that was basically it for the electrical stuff. Now let's talk a little bit about switch debouncing, a little bit. So if you have a switch, any mechanical switch, right? Focus. If you have the microcontroller circuit in this box is basically this, right? Switch to ground, and microcontroller has a supply power. The switch is closed. If I press the switch is closed. What you see, if you have V logic, let's say that, and 0. If you look at what's going on at this point, at the start, the volt, let's say there's an internal pull up in the microcontroller, which there is, right? So at the start, when the switch is still open, the switch voltage is basically the supply voltage of the micro, which is V logic. Okay. If you close the switch, you will see the switch start to bounce around, and eventually the voltage will reach, well, near 0 or 0, and that's fine. But in the meanwhile, if you would take literal samples, periodic samples of the voltage at the microcontroller's input pin connected to the switch, you would see erratic behavior, and you would see not one nice edge, or you would see, instead you would see multiple edges. So what we do is, there are several methods for solving this. One is with an RC, a low pass filter applied at the switch. Another one is with flip-flop, I think. There's a lot of stuff. What I usually do, if I need a microcontroller anyway, is just do it in software, because it's, well, I like it better. You have much more control over it. If you want, you can tune it per switch, type switch. Actually, if you're interested in that, this Jack Gansel, that's Gansle, if I'm not mistaken, made a very nice blog entry or an article about this, different switches and their debounce or bounce behavior. And if you search for Jack Gansel debounce, you'll probably find that. It's very interesting and surprising even. So I like to do it in the software, and how that works is this. I make like an event handler that fires every 2 milliseconds, let's say that. I have a shift register in software, just an 8-bit value, where each 2 milliseconds I shift in the pin voltage that we just saw, which is 0 if the switch is closed, or 1 if the switch is not closed, and the bit that falls out here, simply discard it, right? So what you have here is a history of the last 8 samples, the last 8 2 millisecond events where the switch voltage was sampled, basically. And if you call that register hash, then what you can do every 2 milliseconds is I'll use some creative C-like pseudocode here. It doesn't really matter. It's very seems to differ from video to video. It's not a big deal. First, shift the register one side to the left, so the most significant bit falls off. Then shift in the pin voltage. You can remember that the 0 volts corresponds to a closed switch. Then, if hash is 0, then button down is true. Right? Else, if hash is 255, in other words, all bits are 1, button down is false. Right. So what this says if the last 8 samples have all been 0, in other words, the switch has been closed, the last 8 times we looked, we can be pretty sure that the switch is actually closed and all the debouncing has happened already, right? Else we would see something else, something other than all 0 bits. So, and then we would change state variable, let's say that button down contains a state of the button, filtered state of the button, the debounced button, we set it to true. So then the switch is set to be down. Likewise, if there's 8 samples of high voltage, in other words, the last 8 times that we looked, the switch voltage has been high, in other words open, we can be pretty sure that all the debouncing has passed, and we're actually looking at an open switch, and that's the right moment to call button down false. In other words, from then on our switch is not down anymore, right? So we go from a raw pin voltage to a filtered button down state variable. So instead of, well, you know how it works, right? instead of erratic behavior, we go from a filtered variable that nicely shows one edge when going from low to high or vice versa. I wanted to do this because if I use this circuit for example as a manual clock input to a circuit, the last thing I want is that when I press this switch once, there are two edges on the clock input. So I really don't want that, so that's why the whole debouncing goes on, right? So yeah, future of this box, I don't know, it works pretty well. So functionality is pretty minimal. And one thing I needed, or I really wanted, was the polarity switch, which is really convenient, right? And actually this solves most of the cases I want to do with this box. And you can extend it in any way you want. You can emit pulses or make it programmable using switches and a function switch and a latch, like I said, latch digital signals. But if you're doing that kind of stuff, how about we take a scope or we take a function generator, right? So this is a very, very nice, simple solution to simple problems, and it's very convenient. So that was all. Thank you very much for watching. Let me know what you think, and for more info, please see the video description. Right, so have a nice day. Thanks for watching. Goodbye.